Good morning, everyone. Welcome to Math Monday. I'm Miss Barnes, and this segment is for kindergarten through second grade. How's everyone doing this morning? I hope you had a great week. I know this week is supposed to be pretty nice outside, so make sure that you're taking extra care of yourself in this high-stress environment. Today, we are going to be working on a specific strategy called counting on. And we are going to need a number line today. Now, if you don't have one at home, that's okay. I'm going to show you how to make one really quickly. Take any piece of paper. You'll notice mine is kind of small, but that's okay. It'll still work. Take any piece of paper, and I want you to fold it in half, both horizontally and vertically. So you're going to fold it 2 times. I'm going to make the fold for the long edge first, and then I'm going to go ahead and fold it again. Both of these lines are important for getting our number line right. Okay. And then what you'll do is you'll take a black marker and you'll just trace over the line that cuts the paper in half, the long edge. And then in the line on the middle, you're going to make 1 hash mark and mark that as 5. Okay. On the far end, we need a 0. On the left, put a 0. On the right, put a 10. And then in between 0 and 5, you need 1, 2, 3, and 4. And in between 5 and 10, you need 6, 7, 8, and 9. So take a moment now, finish getting your number line ready, and let's get ready to learn. Getting started. Is your number line ready? Like I said, today we're going to be working with the count on strategy. It's a specific strategy, and the tool that we'll use is a number line today. Let's jump right into our first question. Jack sees 7 ducks in the pond. Hannah sees 2 more. How many ducks do they see in all? Do you remember when we learned our strategies for solving word problems that the first step is to read the problem in its entirety? That means the whole thing. Do you remember what that allows us to do? That's right. It gives us what's called context, and we're able to understand the story that the problem is trying to tell us. So here in this story, Jack and Hannah see ducks at a pond. Do you remember a time when we saw ducks at a pond? That's right, we went to Loose Park in August, maybe September. And we saw the ducks and we counted the ducks in the pond there. So let's talk about how to solve this problem. Jack sees 7 ducks in the pond. Hannah sees 2 more. How many ducks do they see in all? Now, when we're talking about using this specific strategy with a number line, we need to talk about a couple different things. First, we're always going to mark in the question where we will start and how many we will count on. So here I'm going to take my drawing tool and I'm going to highlight a couple different numbers, and I want you to tell me what we're going to do with them. So the first number that I would like to talk about is the number 7. Okay. Jack sees 7 ducks. Why is that an important number? Do you know? Well, let's talk about the other number. Hannah sees 2 more. One of these numbers is where we start, and one of these numbers is how many we need to count on in order to find our sum. So where do we start? With 7 or with 2? Let's start with 7. So on my number line, I'm going to put my finger on number 7. When I put my finger on number 7, you will see a green highlight pop up with number 7. So you find number 7 on your number line and put your finger on it. There is my number 7. Now, I'm going to take my pencil and I'm going to count on. When I count on using a number line, you're going to see a hump and an arrow pointing to the next number. That way I know which direction on the number line I'm counting, and how many humps is how many times I have to count on. So let's start at 7, and Jack saw 7 ducks. Well, how many did Hannah see? Hannah sees 2 more. So let's start at 7, and with your pencil or with your finger, I want you to count 1 to 8, and 1 more to 9. So this is 1, that is 1. So altogether, we counted 2 more. Now, what number did we land on? Take a minute and look. That's right, we landed on 9. So what do you think the sum of our question is? What is the answer to our problem? The question is, how many ducks do they see in all? So our answer is they see 9 ducks. How did you do with that one? Are you ready to try another one? Let's see what the next question says. So here's the second question. Are you ready to try it out? Remember, step 1 is to read the whole question. Brandon is picking tomatoes from the garden. There are 4 in the basket. He puts 3 more in. How many tomatoes are in the basket now? So let's think about the problem and the story that it's telling us. The second step is, let's talk about what our answer is going to look like. What is our answer statement going to say? So the question that we have to answer, is how many tomatoes are in the basket now? So our answer statement should say, there are some, so I'm leaving a blank, tomatoes in the basket. That is our answer statement. Now let's go back and read the question a second time and figure out where we need to start and how many we need to count on. Are you ready? I'm going to get my highlighter tool out, and we're going to stop when we get to the second sentence. So, are you ready to read with me? Brandon is picking tomatoes from the garden. There are 4 in the basket. So that tells me that we need to start on the number 4. How many do we need to count on? Let's read the next sentence. The next sentence says, he puts 3 more in. So that tells me we need to count 3. So I'm going to take my tool here, and we're going to count 3 jumps to the right because he's adding. So 4, count 1, 2, 3, and I'll draw my arrow there because that's where I'm going to stop. I'm going to put my finger on the answer to our question. I'd like you to do the same on your number line. Are you ready? My answer is 7. What's your answer? Did you also get 7? Great job. So when we go to fill in our answer, how many tomatoes are in the basket? If you said 7, you're correct. Are you ready to try one more? There's one last problem for you today. The last problem we're going to try together is this problem. Step 1, read the whole thing from start to finish. Anna fills 6 bowls with water. Then she fills 1 more. How many bowls did she fill? Okay. Well, our first step is always to take the question and turn it into a statement. So let's find our question. How many did she fill? So our statement is going to say, Anna filled blank bowls. Remember that blank is there because we don't know how many she has filled yet. We are trying to solve for that. Now let's go back and reread the question and let's find out where we're going to start on our number line and where we're going to end on our number line, or how many we're going to count on rather. So the first step, let's read the first sentence and find out how we start on our number line. So Anna fills 6 bowls with water. Can you find 6 on your number line? What if you can't find 6? Do you think you can count from 0 to 6? Awesome. Let's start at 1. 1, 2, 3, 4, 5. Oh, and there is 6. Great job. Now, when we're counting on from 6, what number do we need to count for? What number do we need to count on? So we need to take our tool and come back to the question and read the second sentence that says she filled one more basket, or bowl rather, sorry. She filled one more bowl. So we're going to start at 6 and we're going to fill one more bowl. And we landed on the number 7. So can you tell me, how many bowls did Anna fill altogether? That's right, great job. Anna filled 7 bowls altogether. That does it for today, friends. You did a great job and you worked so hard. I can't wait to see you next week. It was my pleasure having you in class today. Remember, if you want to show me what you're doing every day in school, if you want to show me the answers to your questions, you can find me on Twitter at MissB_KCPS. We'll see you next week.
Kindergarten is great at Kansas City Public Schools.
I know they have really good teachers. I know this is a great school.
They teach them stuff that I thought my kids would never be able to know at the age of 5.
Since deciding to send our kiddos to a neighborhood school, we've become even more of a part of our community.
Now is the time to enroll your future kindergartner for the new school year. Visit enrollkc.org today.
Good morning. Thanks for joining us for Math Monday. I'm Erin Dorsey. I'm one of the elementary math coordinators for Kansas City Public Schools. The last few segments, we've been working hard solving word problems in math and using the 8 mathematical practices to help us. Today, we're going to continue those lessons using a tape diagram to solve our problems. A tape diagram is a strategy that can be used to solve any word problem. If it sounds new, it's really not. It's very similar to number bonds, and you use number bonds all the way in kindergarten, 1st and 2nd grade to help you solve problems. A tape diagram is just taking that number bond a little bit further. So let's get into our problem.
Let's take a look at our problem. A Kansas City store has 458 sheep shirts, 212 Royal shirts, and 277 KC hats in their inventory. How many more shirts does the store have than hats? The first thing I want to do is identify the most important information that will help me solve my problem. Do you see any information that we could use? If you're thinking this information here, you would be correct. 458 chief shirts, 212 Royal shirts, and 277 KC hats. that information is going to help me solve my missing pieces it's going to help me solve for my missing pieces. Another piece of information that's extremely important is the question, because that tells me what I'm trying to find out. So as I said before, today's strategy is going to be using a tape diagram. Now, you may have heard of this same strategy referred to as a bar diagram. Those are the exact same thing, it just has two different names. So if you hear your teacher or someone else say bar diagram or tape diagram, we're talking about the same strategy. With this strategy, we need to figure out what we're comparing, and we can find that in our question to this problem. How many more shirts does the store have than hats? So what are we comparing? If you said shirts and hats, you would be correct. So I'm going to list those two things off to the side. I have shirts and I have hats. S for shirts, H for hats. For the shirts, I'm going to draw a bar. This is my total amount of shirts. And I know that this total is made up of two parts, and I get those parts from my problem. I have 458 Chief shirts, which is one part, and I have 212 Royal shirts, which is my second part. Together, they give me my total amount of shirts. Now for the hats, I have a total, and that is 277. But if I'm comparing my hats to shirts, that means that my bar for hats needs to be the same size as my bar for shirts. And it's not, is it? I have all of this space here to make up, and that is my unknown. That's what I'm trying to figure out. So the first thing I need to do is figure out what this total is. How do you think I can do that? By adding, exactly. I have two parts and now I need to find the total, and I can find the total by adding. So I'm going to add 458 plus 212, and that will give me my total amount of shirts. 8 ones plus 2 ones is 10 ones. Put my placeholder down, carry the 10. 5 tens plus 1 10 is 6 tens, plus another 10 is 7 tens. And then 400s plus 200s is 600s. My total amount of shirts is 670 shirts. So remember, if I want to make my hat bar the same size as my shirt bar, that means my hat bar also needs to equal 670. Do I have a piece of that total? Yes, I do. 277 is a piece of the total. So I have 670 and a piece. To figure out the unknown piece, I can subtract, and the answer will be my missing piece. So I'm going to go ahead and do that. 0 ones minus 7 ones. Right now I don't have enough, so I'm going to have to break down to 10. That means this would be 6 tens. And I'm going to put the 10 here. 10 ones minus 7 ones is 3 ones. Now I have 6 tens minus 7 tens. I don't have enough right now, so I need to break down this 100. If I break down this 100, this becomes 500s. And I put my 100 over here. So I have 160 or 16 tens. 16 tens minus 7 tens is 9 tens. And then 5 hundredths minus 2 hundredths is 3 hundredths. This is my missing piece. So I'm going to put that back up here. So that means 277 plus 393 equals 670. If we did our math right, all of that should equal. Let's check it real quick. 277 plus 393. 7 plus 3 is 10. 7 tens plus 9 tens is 16 tens, plus another 10 is 17 tens. Carry. 2 hundredths plus 3 hundredths is 5 hundredths, plus another 100 is 6 hundredths. So 670. Yes, it does equal. We got it correct. So let's make sure we've answered our question. How many more shirts does the store have than hats? Okay, well, if the store has 670 total shirts and it only has 277 hats, this missing piece here is how many more shirts it has than hats, and that is 393. So my answer is 393 more shirts than hats. Let's take a look at another problem. The same store sold 304 Royals jerseys in June. I'm going to highlight that because I know it's important. And 34 fewer in July. That is also going to be important. How many jerseys did the store sell in both months? So I need a total. It's going to be for both months. So when I set up a tape diagram, I know that I'm comparing two things. In this problem, what am I comparing? If you said the months June and July, you would be correct. So I'm going to write those down here. June and July. In June, there were 304 jerseys sold. In July, there were some jerseys sold, but it was 34 jerseys less than 304. So that means this right here is going to tell me how many jerseys were sold in July. What operation do you think I could use to find out how many were sold in July? Subtraction, yes. I have a total of 304 jerseys in June, and I know that I sold 34 less than that in July. So therefore, I can subtract. 304 minus 34. 4 ones minus 4 ones is 0. 0 tens minus 3 tens. I'm going to need to break down 100 to do that. So I'm going to break down 100. That means there's going to be 2 hundreds left here. I'm going to put my 100 down here, which is also equal to 10 tens. 10 tens minus 3 tens is 7 tens. And then 2 hundreds minus no hundreds is 200. So in July, they sold 270 jerseys. Am I done? You're right, I'm not done. Because if I go back to the question, it asks me how many jerseys were sold in both months. How am I going to figure that out? That's right. I am going to add my jerseys in June, which is 304, to my jerseys sold in July, which is 270, and that's going to give my total amount of jerseys sold in both months. So 4 ones plus 0 ones is 4 ones. 0 ones plus 7 ones is 7 ones. Or I'm sorry, I made a mistake. Did you catch it? That's right, I was in the tens column, not the ones column, so let's redo that because mathematicians want to be precise. I have 0 tens plus 7 tens, and that leaves me with 7 tens. 3 hundreds plus 2 hundreds equals 5 hundreds. That gives me a total of 574 jerseys sold in both months.
So what do you think? Bar models, tape diagrams, two different names for the same strategy, but it's a strategy that's going to work for you all the time. And it takes your knowledge of number bonds and helps you figure out how to solve word problems that are maybe more complex than what you're used to. The main thing is that you are using what you know in the problem to solve for what you don't know. And that you're using a strategy that allows you to organize your thinking. Now, I'm sure you noticed in the problem, I made a mistake. What did I do when I made that mistake? That's right. I stopped and I went back and I corrected my mistake. I didn't just keep going because mathematicians are precise. One of the 8 mathematical practices is to attend to precision, and that is very important. We attend to precision by making sure that our thinking is organized, that our work is not sloppy and all over the place so that we can understand what we're writing, and that we keep using the right type of language, and we keep explaining our thinking as we go along. All of that allows us to attend to precision while using our background knowledge to solve for what we don't know. I hope you enjoyed your time today, and I hope that when you're solving problems with your teacher, that you can use this strategy to help you. Have a great day. See you later.
I love Southeast because of the culture, the band program, and restorative justice.
I love Southeast because of the academics, sports, and students.
I love Southeast because of the people, the energy, and the advanced classes.
It's not alike. I love Southeast because the students here at Southeast are full of potential and they believe in achieving anything.
We are Southeast.
Southeast.
We stand shoulder to shoulder.
Join the Southeast family. Enroll today.
Hello, my name is Mary Jo Fender and this is Math for Middle School. Today we're going to be going over how to use laws of exponents to multiply monomials. What you'll need today is paper and pencil. Okay, take a quick second to get ready to learn. We're going to talk about laws of exponents, particularly the product of powers. And our goal for today's lesson is to use laws of exponents to multiply monomials. You might be asking yourself, okay, well, what is a monomial anyway? And a monomial is an algebraic expression consisting of one term. And I have 4 different types of monomials. They can be as simple as x or 49, or you can have the variable term 3x. You can also have 4x cubed or 4x to the 3rd power. These are all single term expressions. You might be asking yourself, okay, well, what is a term? A term is either a single number, variable, or numbers and variables multiplied together. Terms are separated by addition or subtraction signs, or sometimes by addition. Now I have an equation here, 7x minus 4 equals 17. I've drawn red boxes around each of the terms to show you. Notice the part on the left, that expression, the terms are separated by a subtraction sign. So let's take a quick moment and complete a T-chart. to see if we can classify monomials. So draw your T-chart quickly. On the left-hand side, write the term monomial. On the right-hand side, write your term non-monomial. We have 6 expressions to sort. I'll read them to you and put them in the category that you think they belong. The first is X. The second term or expression is X minus Y. 3x to the 5th power. 7x y squared. 15 y plus 2. Okay, hope you have those all sorted. Let's go over them very quickly. So the variable x is a monomial. It's a single term. There's no addition or subtraction involved. The second one, x minus y, is not a monomial. Remember, monomial means expression with one term. Well, x minus y has 2 terms. It's the 2 terms x and y are separated by a subtraction sign. The third, 3x to the 5th, is a monomial. It's a single term, no addition or subtraction to separate the terms. 7xy to the 2nd power. That is also a monomial. The number 15 is a single term, so that is a monomial. And y plus 2 is 2 terms. The y and the 2 are separated with an addition sign. I hope you got those right. If you did, pat yourself on the back. Nice job. So let's continue. Product of powers property. Well, we talked about powers the last couple of times, and we know a power is created using a base and an exponent. The term product means to multiply. So what if we are multiplying 2 powers together? So the term or the phrase simplify just means to write in the fewest number of letters or the fewest number of terms. So if we remember that 4 to the 2nd power is really 4 times 4, and our second power is 4 to the 3rd power, remember when we extend that out, that's going to be 4 times 4 times 4. Now we have repeated multiplication all the way through. So if we count up those 4s quickly, we notice that we have 5 of them. So we're going to put our base of 4 back. Because we're multiplying 5 4s, we're going to put the 4 to the 5th power. So we can say 4 squared times 4 cubed is equal to 4 to the 5th power. Have you noticed a shortcut? There is one. And let's do one more and see if you see it, because this is the background for the product of a powers property. So our example here is 3 to the 4th power times 3 to the 3rd power. So if we extend 3 to the 4th power out, remember that's 3 times 3 times 3 times 3. And if we extend 3 to the 3rd power out, we're saying 3 times 3 times 3. Now we're multiplying all of these together, so I'm going to put parentheses so you can see which set of expanded notation goes with which power. Because we're using repeated multiplication, we can write this, we can count the 3's up. Notice there are 7, counting left to right. So that's going to represent my exponent, and my base is going to remain the same, 3. So we can say 3 to the 4th power times 3 to the 3rd power is actually 3 to the 7th power. Did you see the shortcut yet? Or why product of powers works? If you notice, if I add my exponents together, what's 4 plus 3? I hope you're saying 7. Notice the 7 is the same as the 7 in my simplified version, 3 to the 7th power. The product of powers property says if I have the same bases in my powers, all I have to do is simply add my exponents together. And we can verify that by actually looking at our expanded form for proof. Let's try another one. This time I'm going to give you a couple seconds head start. So we're going to continue to use product of powers property, and I want you to simplify 5 to the 4th times 5. Do you see an issue? You might be saying, well, there's no power or exponent on the second 5. Well, there is one. It's implied, and it's an implied 1. So you can still use our shortcut or our powers property by recognizing that that invisible 1 is there. So remember our product of powers property says all we have to do is keep the base and add our exponents. I hope you added 4 plus 1. That equals 5. So our simplification of our expression is 5 to the 5th power. It's not as hard as it seems once you get the trick. One more time, give you a couple seconds head start. Simplify x to the 4th times x to the 2nd. Good job. You added 4 plus 2. 4 plus 2 is 6. So the simplification of our expression is x to the 6th power. Let's try it one more time, but this time let's add coefficients. Coefficients are the multipliers in front of the variables. Now there's a trick to this. We have to multiply our coefficients together, and then we have to multiply our powers together. So the way this would look is I would multiply my 3 times 2, and then I'm going to multiply my x to the 2nd power times x to the 5th. Now I know -3 times 2 is -6. I now know, using my exponents property, that I can say x to the 2nd power plus 5, thank you, is x to the 7th. All I have to do is put my coefficient and my power back together, so that would be -6x to the 7th, to have my simplification of my expression. One more time, very quickly. Give you a couple seconds head start. Okay, good job. Take your coefficients. 2 times 4, yep, that's 8. Multiply your powers. Now remember, the x in the 2x doesn't have an exponent, so there's an imaginary 1 there. So we're going to say x to the 1st times x to the 5th. Okay, so we're going to say x to the 1st. Oh, let me erase that and try that again. So I'm going to say x in parentheses, or in my exponent, 1 plus 5. That's going to equal x to the 6th. Take and put my terms together. That's 8x to the 6th power. That's my answer. Now it's your turn to practice. I have 3 practice problems for you, each of them involving the product of powers property. Simplify, that means to write in the smallest amount of terms. Make sure that you're writing as powers and using exponents. I'll read the problems to you so you can write them down. 6 to the 5th power times 6 to the 9th. 12 to the 3rd times 12 to the 4th. 4x cubed times 5x to the 5th power. Good luck. Keep practicing. That concludes our lesson for today. Let's have a quick review. Today you learned that when you multiply powers with the same base, you can add the exponents together and arrive at the same product. Remember this week to work on your product of powers property so you can continue to improve. It's been my pleasure to have you in class today. I'm Mary Jo Fender. See you next week.
I chose manual because it's challenging and fun and it can help me with college.
I chose manual because I wanted to get a jump start in my career with culinary arts.
I chose manual to acquire skills I'd use in real life.
I chose manual because I want to be an ER doctor and be an EMT is my first step.
Kickstart your future today at Manual Career and Technical Center. Manual is open for all 11th and 12th grade students in both Kansas and Missouri. Learn more today at enrollkc.org/manual or call 816-418-5200.
Hello, my name is Marcelina Lirius and welcome to Math Monday. Today we're going to review a lesson in Algebra 1 and our students in Algebra 2 would find this very useful. You will need some supplies and I'll give you a few seconds to get your pen and your notebook. And when you're ready, let's get started. At the end of this lesson, you should be able to find and interpret key features or key characteristics of functions using graphs. Let's start with the vocabulary words. These words are the key features of functions. I want you to write this on your notebook and choose 3 words. Then describe in your own words or give your own definition. You can draw a picture or any representation that you can associate with the word. Okay, let's start with the first word, domain. And let's see how close your definitions are to these mathematical definitions. So for domain, we're referring to the set of all possible values for x. All possible values for x, or also known as input values. So if we are given a graph, to find the domain, we look at these points here, okay? What are the possible x values? If we extend this graph in both directions, what are those x values? Okay, what are those x values? Then, the range is the set of all possible values for y, also known as output values. Okay, if we extend this line in both directions and look for the values for y, okay, for these points here, what are the values for y? Okay, then looking at this graph, our range here will be from negative infinity to positive infinity. This could be extended in both directions. In the second graph, okay, if we look at the domain, what are the x values? What are the x values? If we extend this in both directions, what are those x values? Okay, that would represent the domain. And for the y values, notice that, okay, this graph starts from negative numbers or negative infinity if we extend this. And it goes down, and the lowest point or the lowest value for y, or for the range, is at this point. So our range would start from this, from negative infinity up to this value. Okay. Then let's look at the next vocabulary words. So the X-intercepts. So the X-intercept is the point where the graph touches the x-axis. To find the X-intercept, okay, I want you to draw this, sketch this on your paper or on your notebook. Draw a line from left to right, okay? Draw a line along the x-axis and stop where the x-axis would intersect the graph. This point here, which is the intersection, is called the X-intercept, okay? It's the point where the graph touches the x-axis, and we denote this X-intercept here, this point, by a comma 0, where a is the value or the X-intercept here. If we look at the second graph, let's do the same thing. On your paper, sketch this graph, and let's draw a line from left to right, okay, there. Notice this is a point of intersection between the graph and the x-axis. So we call this another X-intercept, or one of the intercepts. And if we continue, there's another X-intercept for this graph. Okay, that's how you find the X-intercept for a given graph. And the interpretation is, these are the points where the graph and the x-axis, where the graph and the x-axis intersect. Okay. Ready for the Y-intercept? Okay. The Y-intercept is the point where the graph touches the y-axis. Okay. If we look at the first graph, which is a linear graph, to find the Y-intercept, let's draw a line on the y-axis and, okay, find the point of intersection. So this point of intersection, this is when x is 0 and y is some number, and we call this as the Y-intercept. Let's find the Y-intercept on the second graph. And to find this, let's draw a line along the y-axis. Stop here. Notice that this graph and the y-axis intersects at this point, and we call this point as the Y-intercept. Okay, the Y-intercept. Okay. For the axis of symmetry, for a graph, okay, the axis of symmetry is the line that divides the graph into two equal parts. Each part is the mirror image of the other. For a linear graph, the line of symmetry is actually the y-axis. This will divide, because we can extend this in both directions, and this y-axis, which is the line x equals 0, is the Y-intercept. I mean, is the axis of symmetry. Okay. Let's find the axis of symmetry for this second graph, which is the parabola. Again, it's the line that divides the graph into two parts. Okay. For a parabola, the axis of symmetry passes through the vertex. And if we draw this line, okay, this line will divide this graph into two equal parts. Notice that the right side is a mirror image of the left side. So the axis of symmetry is the line x is equal to some number a. Okay. And for some graphs, you might have a maximum or a minimum value. In this case, for our parabola, okay, the maximum value here, Okay, if we extend this, this will be, we don't have a maximum value here, but we do have, okay, the smallest value for y, which we call the minimum. Okay, the minimum, notice this is the y-axis, and the lowest point on the graph, this point here, y equals some number, which we call b, is the the minimum. Okay. I'll give you a few seconds to take down notes and also create a mental picture of these words with the illustration on the graph. Okay, let's have our first example here. Find and interpret the key features of the graph. This graph is a parabola, which is a graph of a quadratic function. So the parabola faces downward. Then let's look at the domain. Okay, sketch this on your notebook. And to find the domain, I want you to stretch your arms here from left to right. Okay, how far do you think would this graph extend? So what are the possible values? So you're looking from left to right. So in this case, this parabola will actually, the domain will actually be from negative infinity to positive infinity. This could be extended in this direction here. Okay, however, the range, notice that if we look at the range, these are the y values. So we're looking at this y value here, y values, y values. But notice that we have our y value would end at this point here. So our range will be from, if we count here, this is 1, 2. So this will also be, okay, if we find the point here, this will be the point. Okay, this is 1. This will be 1, negative 1 here. So this is the maximum value for y, or the maximum value for our range. So our range will just be from negative infinity up to 2. Or in interval notation, we could write this as y is less than or equal to 2. Follow? Domain are the set of possible values for x. Range are the possible values for y. Now let's find the x-intercepts. Sketch this again on your graph, on your notebook. Okay, to find the x-intercepts, let's draw a line along the x-axis. Okay, this is our line here, and let's stop at the point of intersection. So this point here is called an x-intercept. And we can find the coordinates of this point, which is, so this is 1, 1, 0. So the x-intercepts, you have 1, 0. And if we continue, let's draw and do this also in your notebook. I'll stop here. This is another point of intersection of the graph of the parabola and the x-axis. So this is another x-intercept, and if we find the coordinates, this is the point 3 and 0. Okay, so we have two x-intercepts here, 1, 0, and the point 3, 0. Okay, let's find the y-intercept. In your notebook, I want you to draw, okay, a line along the y-axis, okay, along the y-axis, and stop where the graph and the line would intersect, okay. So this is the point, okay, this is the y-intercept here. This is the point of intersection between the y-axis and the graph. And let's find the coordinates of this point. So this is 0, this is negative 1, negative 2. So this is at the point negative 3 for y. So therefore, our y-intercept is 0, negative 3. Our interpretation again for the y-intercept is, it's the point where the graph touches the y-axis. Okay, Then let's find the axis of symmetry. To find the axis of symmetry, we're going to find the line that divides the graph into two equal parts. Each part is a mirror image of the other. Okay, this is the line which we call the axis of symmetry, which passes through the point x equals 2. So our axis of symmetry, the equation of the axis of symmetry is x equals 2. Okay, x equals 2. It passes through that point, x equals 2. Ready for the next one? Okay. Then, since this is a parabola facing upwards, downwards, I mean, we have a maximum. The maximum point is at the vertex, okay? The maximum point is at the vertex, and the maximum value for this is 1, so this is 1. So maximum is y equals 1. That's the maximum value for y, okay? And we don't have a minimum because we extend this in this direction. This could be extended to negative infinity. Okay, you can take down notes. Now I'll give you one item for practice to find the key features and interpret also this feature of the graph. So that concludes our lesson for today, and I hope to see you next week.
The desire to create lives within each of us. From Grammy-winning producers and musicians, to NBA stars, to Navy admirals and Medal of Honor recipients, to internationally renowned artists and beloved local muralists, Paseo graduates have been creating their own success, their own history, their own legacy since 1926. Now it's your time. Create your future at Paseo Academy of Fine and Performing Arts. Learn more at enrollkc.org/Paseo.